In this video, we're taking a look at gravitation, specifically gravitation when we're talking about big distances, large masses. We're going to look at the history a little bit, and obviously from a limited perspective. Some key touch points, though, that I think are interesting. And then we're going to look at Newton's law of universal gravitation. As is usually the case when you're talking in the Western world, the Anglo-centric world, we start our scientific and philosophical discussions in Greece with Aristotle and the like. And so kind of the last line here, all matter seeks its natural position, was kind of the prevailing idea of why things fell, for example. That, a rock wanted to be on the ground with other rocks, therefore that's why it fell. And obviously that's not really kind of what's going on. And the limited, observation without tools of what was going on in the sky sort of implied that the Earth was there and things were moving around it. And that was the model that they used. A slightly more nuanced version of this came out of what is now India, Brahmagupta in the 5 to 600s BC. The idea that gravity was a force of attraction, right? Then this idea that it was attracted toward the center of the Earth, which is something we now understand about how gravity behaves. This is one of the earliest recorded kind of statements of that, which is interesting. We go back over to the Western Hemisphere, Ptolemy in Egypt, I guess Eastern Hemisphere, whatever. The divisions are arbitrary. But Ptolemy and the Ptolemaic view, which pervaded thought in Western Europe for a long time, especially through what we would call the Middle or Dark Ages. He also was about the geocentric model, that the Earth was at the center of the universe. And of course, we're not just talking about like a system, right? The entire universe, right? Thinking about what you can see, stars not seen as individual objects, but really just almost pin pricks in, a static space. But in order to account for the fact that things didn't move in perfectly circular orbits around the Earth the way the models wanted them to, he added these things called epicycles, which were little circles around circles. And it was incredibly complicated. And it was decent in terms of that he was trying to address some of the things that we saw that didn't match up with things just going in orbit around the Earth. But he was still missing the mark. If we go to what is now, I guess, Turkmenistan, it was then Persia, the fact that gravity forces vary with distance was an idea that was kind of being tossed around, which is a pretty important thing that we now know to be true. And certainly, if you know anything about Persia during this time, huge amount of mathematical work was being done and scientific work that carried, thought very far forward from what was going on in other parts of the world. So that's a pretty interesting idea as well. Our story usually goes to Copernicus, and usually it jumps from Ptolemy to Copernicus. If you're talking about kind of a European perspective, he was from Poland, and he said, no, it doesn't make any sense that everything orbits around the Earth. If you just put the sun at the center of the universe, and again, universe here, not solar system. Later we would say solar system. You've got Mercury, Venus, Earth, Mars, the moon around Earth, Jupiter and Saturn, as much as were as kind of commonly understood in our solar system. And then some stars were sort of fixed there and we all moved, and that's why things appeared to move. But this wasn't published until after his death, right? Very much the heliocentric solar system. And I don't know how many of you have gotten a chance to watch Cosmos, either the older Carl Sagan version or the newer Neil deGrasse Tyson version, just talking about the scale and our understanding of kind of the heavenly bodies as they were described, but the cosmos as we would think about them now. Tycho Brahe was not a Copernican. He was kind of famously a character. So if you want to read some fun stuff about the goings on in the royal courts and among nobility, but also with some science thrown in, read about Tycho Brahe. But he wanted to, it seems, in part to appease all of the people in power at the time, that he was kind of part of that class and didn't want to upset people. He said, well, yes. It turns out that the Earth is at the center, but the moon and the sun go around the Earth, and everything else basically goes around the sun. which, if you know anything about relative velocity, which we've talked about in at least 1 and 2 dimensions, this isn't actually the most terrible way to think about it. I mean, it is way more complicated than necessary, but you can get perfectly reasonable and accurate model of the solar system doing this, because if we call ourselves the fixed point and measure everything around it, as long as you don't try to jam all the other planets as going around the Earth and the sun, what's the difference between one orbiting the other? Really, you've just picked a reference point. So not terrible. And it really took Kepler, who worked for Tycho Brahe in his observatory, and took really detailed measurements of the motion of some of the planets, and started to say, oh, there's not only is the sun definitely at the center of this whole system, but it's not just perfect circles. Everything's actually going in an ellipse. Now, this diagram that you see here is kind of stretched and exaggerated. Especially the inner planets are pretty close to circular. And then we get to very familiar names to us in physics this year, Galileo and Newton. Galileo famously was one of the first to use a telescope for astronomy. Telescopes existed for other things, but one of the first to try to use it to see things in space, some of his discoveries. And so he was like one of the public advocates in Europe for the heliocentric model, the idea that the sun was at the center. But he struggled with why we didn't experience Earth's motion if it was. He, of course, very famously was tried for heresy during the Inquisition. Then there was Newton. The law of universal gravitation. The story, of course, is that he goes to the country to escape the plague. He sees an apple fall to the ground and sort of has this revelation. Probably not true. But certainly in his explaining of his thought process, he says, okay, the apple accelerates, so a force must act on it. That was something, if we think about what we now call Newton's 3 laws of motion, the second law would imply that this is true. Where does that force come from? Right? We also observe the moon orbiting around the Earth. So there must be a force because it's going in a circle. It's accelerating. Where does that force come from? And so his big idea, putting this all together, the great synthesis, the leap to the stars, as they were sometimes called, is that all of this was the same force, the force of gravity, pulling everything toward the center of the Earth. The thing that pulled the apple down was the thing that held the moon in orbit. And the other big part of this idea was, well, how would we determine this force? And that it depended on the masses that were involved, right? It is proportional to mass 1 and mass 2, their force going together. And one of the arguments for this was looking at tides. Why is it that the water rises and falls as sort of in some relationship to the position of the moon? It seemed to be that, well, it couldn't just be the Earth pulling on the moon. It would also have to be the moon pulling on the Earth. And the part of the Earth, the water that can kind of move around, is the thing where we see that. And then also the inverse square law, 1 over r squared, as an idea of how this kind of depended on distance. This was a pretty educated guess. He didn't have the technology or the mechanical devices to test this, but it was good, and it is indeed correct. We also see this inverse square law in lots of places in the physical world, so it was a reasonable thing to assume. The inverse square law basically comes from this idea that if there's this gravitational field, as we call it, and then the gravitational force would pull you in toward the Earth. So you've got a bunch of lines pointing inward toward the Earth. And then these red circles show places where the force would be the same, and they're kind of getting bigger and bigger. But they're not actually circles, right? They're just a slice of a sphere, because this is 3-dimensional. And if you think about the force of gravity depending on sort of the number of force lines or field lines divided by the surface area, well, the surface area of a sphere depends on r squared. And we also see this with light and sound and the electric field and other things. So this was a good idea. So here we come to Newton's law of universal gravitation. The big premise, he said, was that the force of gravity was proportional to the two masses involved and inversely proportional to the center-to-center distance squared between them. So there you go. Newton needed two things. He needed some evidence of this, and we'll talk about that with the apple and the moon and Newton's kind of mountain arguments. But then he also needed to figure out what constant was there. It was not enough just to have a proportionality. We needed to get some numbers. And so big G was not actually measured or determined until a little bit later. Henry Cavendish has a fairly famous experiment where very, very precise devices, isolated from everything you could, a torsional pendulum. But basically you have two masses, right? And you can measure how much the pendulum sort of shifts when they're there so that you can figure out what's going on with them to figure out the force of gravity. And he calculated big G, 6.67 times 10 to the negative 11th Newton meter squared per kilogram squared. And, we've refined this number over the years and come up with other pieces to the puzzle, but that's still a really reasonable number. And then he could find the mass of the Earth once he's done that, because he was able to, know one of the masses in that equation. The other idea that's important is this idea of superposition, that if you have multiple massive objects, that they're all pulling on each other, right? And this is what makes gravitation actually more complicated than just the Earth pulling down on us. And so, if you set them up in kind of this simple thing, you could ask, what is the net force on mass D from all of the other masses? Well, it's going to be pulled by A, B, and C. If they're all 1 kilogram masses, then A and C are equal and opposite. They're opposing each other, so they're going to cancel out. And it's really just that force of gravity that B is applying that matters, and you can get the value. You'll notice, hopefully, how small the force of gravity is on these from these 4 1 kilogram masses on each other, and that has a lot to do with the fact that gravity is a pretty weak force. It needs very big masses over it works over long distances, of course, but it doesn't take that much to take you or me and get us to a place where the force of gravity of the Earth's gravity is small enough that we barely notice it. You go out to the moon's orbit, we are more attracted to the moon than to the Earth. So that's kind of an important idea. Another interesting thing to think about is what we call shell theorems, and these will come back when we look at electricity too. But if you imagine standing on the surface of the Earth, we experience a force pulling us toward the center of the Earth. But of course, when you're outside, right, it doesn't really matter if the mass is actually all at the center or if it's spread out perfectly evening in a uniform density sphere, or if it's actually just a shell on the outside. It would still pull you toward the center. And it doesn't really matter. And that's because all those little pieces would kind of add up to get you there. But once you go inside a shell of mass, then you're being pulled toward all the pieces of it. And this is only 2 dimensions of it. It's actually in 3 dimensions. But the mass you're really close to with the small r dominates that. And then you've got all this other mass that's out there, but it's a bigger r away. And so no matter what you do, the sum of the force from all the bits of mass are 0. So if you could actually hollow out the Earth and go inside of it, you just float around, not feeling any net force from the Earth. So you need to have a conceptual understanding of these two kind of shell theorem ideas. And we'll look at what happens if you take something that is solid like the Earth and you actually tunnel in. As you go in, the mass above you acts like a shell and the mass below you acts like just a smaller planet. More on that later. So Newton's law of universal gravitation. If you've got particles, shells, spheres, and you're outside of them, you just use Fg equals gmm over r squared. But if you have non-spherical extended bodies, you need to add up the effect of the little bits of mass using an integral form. And we'll come back to that as we go through this. So that's it. Kind of an overview of how we have in part thought about gravity throughout history, or at least some of history and some people. And then, of course, Newton's law of universal gravitation and how it behaves.